So last class we learned the power rule. Today we're going to learn the product and the quotient rule. If you remember from last class, I told you that the power rule doesn't work over multiplication. It only works over addition and subtraction. And we can kind of confirm that it does not work. If I took the derivative of this product, I can see if it's going to be equal to the derivative of the first part, which is just 3, times the derivative of the second part, which would be negative 8x. The way I could check that is to simplify first. Before I take my derivative, I'd get negative 12x cubed minus 8x squared minus 9x minus 6. Okay, and that is my function simplified, and I can take the derivative of it and see that f prime is not going to be equal to 3 times negative 8x. These are not the same. So this is wrong. So we need a new rule to be able to help us with products, because you might be thinking, well, I'm just going to have to simplify whenever I see a product. Well, if I have something like this guy right here, I don't want to simplify that. Or if I have something like this guy here, I can't simplify this. I cannot multiply this x cubed by this x. This x is trapped by the clutches of the cosine and will not be released from cosine until we get rid of cosine, and can't get rid of cosine. So I have a product here, and I can't take the derivative as of right now because I can't simplify this. So we need a new rule to be able to easily take the derivative of this and to take the derivative of this. And the power rule is the following. Oh, sorry, the product rule is the following. We have two functions being multiplied by each other. The derivative is, and I'll usually say the first one is being the f and the second one being g. Now, my product rule looks different than the product rule that will be shown on the odd answers in your book or that you would find somewhere else online. It's the same. However, I do it a little bit differently than the book because it kind of lines up a little bit nicer with the quotient rule. The product rule is the derivative of f times g is equal to the derivative of f, or the derivative of the first, times the second, plus the derivative of the second times the first. Okay. Since it's multiplication, since it's addition, you can flip-flop things a lot of places, but I like it like that. Okay? All right. So before we go back and check to make sure that it's correct, I'll show you just like the application of this product rule for this g. And I want to find this product rule at x equals 1. Why don't we just say x equals pi for this g? So let's write down g of x, and let's find the derivative of it at pi. Here's how it works. We would first denote our product of our two functions. I usually use parentheses. That way I know I have a little f and a little g. Okay, and yes, this is g, but I'll just kind of denote this as this is like f and this is g. And the derivative of g is g prime would be equal to the derivative of f times g. That'd be 3x squared times cos x plus the derivative of g times f, or the derivative of the first times the second plus the derivative of the second times the first. Okay, and it might be helpful just to put parentheses around this x cubed or to move this x cubed in front of the sine x. That way you know you can't multiply the x cubed by the x. Okay, now this is a messy derivative, right? It's like kind of large. There's multiple parts. However, it is a derivative. This is our helper. This is our tangent slope generator. This has feelings too. You can simplify it if you want to, but I will let you just write this and leave it like that. This is totally fine. You will be able to plug in values into this derivative and get slope values of your original g. So if I wanted to find the tangent slope to g at pi, I'd plug in pi, which I can do. 3 pi squared, the cosine of pi is -1. Sine of pi is 0. So I'd get that the tangent slope to this function at pi is -3 pi squared. Okay? Totally cool. Well, let's go back to our original guy, this 3x plus 2 and the -4x squared minus 3. Maybe we didn't want to simplify when we took this derivative. Maybe instead, now that you have this product rule in your arsenal, you say, you know what, I'm just going to use the product rule. Let's see if we get the same thing. Well, here we go. I'll get f prime is equal to the derivative of my first, which is 3, times the second, plus the derivative of my second, -8x, times the first. What you might not be able to see, but if you simplified could see, is that these are the same. And what I will tell you is that I don't care which one you put as an answer for a derivative. This is the same as this. I'll show you. -12x squared minus 9 plus -24x squared minus 16x. -12x squared and -24x squared give me my -36x squared. I have -16x and I have a -9. It's the same, okay? I will accept either answer. It's okay that you don't simplify, okay? It's okay. Your book will simplify your homework problems and the odds all the way down. And if they have like trig functions, they do some crazy trig simplification using some crazy trig identities. You won't have to be concerned with that, okay? You can just leave your answers after you take your derivative and just say, I'm good to go. Because let's look at the derivative of this at x equals 1. This is going to be messy, but it's kind of simple to take the derivative using this product rule. We'd have the derivative of the first times the second plus, let me shrink this a little bit, the derivative of the second, which would be 3x squared times the first. That's long. That's a big derivative. But it is the tangent slope generator for that product of x squared minus 3x plus 4 times x cubed minus 2x plus 1. It has feelings too. You will be able to plug in values into this to find tangent slopes of my original function. This is fine. Okay? So if I wanted to find f prime at 1, it would be -1 times 1 minus 2 plus 1, which is 0, plus 1 times 1 minus 3 plus 4 is 2. And this would be 2. You do not have to simplify to be able to plug in values. So understand that. Now, it's very important, and we're just going to look at this guy on the left, to understand when you should use the product rule and when you shouldn't. Let's take a look at 2x cos x minus 2 sine x. And in particular, just the 2 sine x. Let's look at this as, let's put this as x and this is x. Let's look at just this little piece I'll call, I won't even call it g. I'll just say, let's just take the derivative of negative 2 sine x. Remember that if you have a constant times a function, and you want to take the derivative of the constant times the function, you can just leave the constant and multiply it by the derivative of the function. Though you look at negative 2 sine x and you see a product of two things, sure, it's a product. If you did the product rule for this, you'd be wasting your time, because the derivative of this would just be negative 2 cos x, right? It's just a constant times a function. However, I will show you that the product rule will work for this. Let's treat the 2 as a little f. Let's treat the sine as the g. What's the derivative of negative 2? 0 times g, so that's f prime g, oops, sine of x, plus g prime, that's cos x, times f, negative 2. We get the same answer because 0 times sine of x is equal to 0. We're just going to have that. This was very unnecessary to do. So whenever you see a constant times a function, don't use the product rule. It's only when we have two functions like stuff with x's multiplied by other stuff with x's, like a trig function times something like 2x, that's when we have to use the product rule, because I cannot simplify 2x cos x. Okay? So I can go ahead and, why don't you guys do this? Find the derivative of f at pi. Everybody, please do it. I'm asking you to do a problem. Do the problem. See if you can get it right. Don't just wait till your homework to actually do some math with this product rule. Yes? Plus a negative. Plus a negative. Everybody do this. Everybody get it done. Find the derivative at pi. F prime g plus g prime f. Two x is your little f. Cosine x is your g. F prime g plus g prime f. And then we have to add the derivative of negative 2 sine x, which is what we did over here, negative 2 cos x. Our answer at pi is 0. Our answer at pi is 0. We need to get the correct derivative first. Check your answers with a neighbor. Please help each other out. There are some people that are unsure of where they're going. If you got 0, good. Help somebody else out.
2 cosine x plus 2x times negative sine x minus 2 cosine.
Now you just need the derivative of that. Next. Now you just need the derivative of this piece next to that. This is correct for that, but now you need the derivative of that.
Like if you, because this just turns into
Cosine.
yeah.
So it'd be negative 2 cosine. Okay. And that would turn into positive 2. Right. Which is what you have. Okay, good. Just making sure you had it all down. You good, Jerry?
Sure.
All right. Good. Fantastic. Okay. So, key is to keep things organized, to keep your work neat. A lot of people, when they do a product rule, they'll just stop here, and then they forget to take the derivative of the last piece, okay? What you'll find is that the 2 cosec and the negative 2 cosecs will cancel. You'll just have negative 2x sine x, all right? All right, so that's the product rule. Let's talk about the quotient rule. I told you last class that you cannot take the power rule and apply it over division, which is why this is not true. The derivative of 3x squared plus 6x plus 9 divided by 2x is not 6x plus 6 over 2. And hopefully on your quiz, when you saw your problem like this, instead of taking the derivative using the power rule, you simplified first. You had homework problems just like that. I assumed you guys knew how to do it because nobody asked about it. So now that we've simplified, we are able to take the derivative and get the correct derivative. 3 halves plus negative 9 halves x to the negative second. That's the correct derivative. That is not 6x plus 6 over 2. This is not the same. So you might be thinking, all right, well, whenever I see a division problem, I'm just going to simplify first and then use the power rule. Well, sure, that's all fine for something like this. But what we will see is that we don't have functions that can be simplified by dividing. Like x over x squared plus 1. We cannot divide this and change this to make it just stuff being added together. So this is a quotient. It remains a quotient no matter what I try to do. Same with g. If I have sine x over x squared, I cannot simplify this. So as of right now, we can't take the derivative of these functions unless we have a new rule, the quotient rule. The quotient rule, you will find that the quotient rule and the product rule are very similar, at least at the top. If I have, I'm going to put f up top divided by g. Okay, the quotient of two functions. The derivative is, the top will look similar except for one difference. The derivative of f times g, or the derivative of the top times the bottom, minus, instead of plus, the derivative of the bottom times the top. all divided by the bottom squared. It's a little bit more intense. Both of these rules can be proven using the magical formula that we generated, and using some math, you can see the proof if you wanted to, but pretty much just take my word for it. This is the quotient rule. Okay? What's great is that, yes, when you simplified this, you could take the derivative. But let's say I didn't simplify this and I just went straight to the quotient rule. This is what my derivative would look like. The derivative of the top, 6x plus 6, times the bottom, 2x, minus the derivative of the bottom, 2, times the top, 3x squared plus 6x plus 9, all divided by 2x squared. What you may not see, and you definitely can't see right now, you'd have to do some work, is that these two are the same. They're the exact same. One is just much, much different than the other, but it's just appearances. If you plug in values for x into this, you will get the same values if you plug in x's into that. And what I will tell you is that both answers are completely correct. You can list a derivative off like this, and that's correct. You can list a derivative off like this, and that's correct. Yes?
On the AP test, do you know which one we're more likely to see?
Probably neither. Probably what you would be given is a question that involved finding a tangent slope at a point. So you'd have to plug in, say, the value 1. You can plug in 1 to either. We will find when we do one other rule in the future that we will have to definitely simplify, because there's always questions that involve simplifying using the other rule. Okay? But these, totally fine. Okay? So to finish off, let's take the derivative of these using the quotient rule. You guys do it while I do it. We'll check our answers. And then there will be extra problems, examples that I will do, which will be on the video. And if you're doing your homework and you're struggling, I advise you to watch those problems. It's all about the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. It may look funky, but it is a tangent slope generator, and it has feelings too. Probably you will have to simplify something like this, but that's easy to simplify. This is just 2x squared. X squared minus 2x squared can be simplified to be negative 1x squared. So that'd be like 1 minus x squared plus 1 squared. This would be an example of a problem. Okay? I'll show you G prime as well, and I will show you examples on the video that you can watch at home. All right, the 24th minute, let's begin doing some extra problems, okay? First problem, find the instantaneous rate of change of the function at x equals 0. So that's the slope of the tangent, that's the derivative at 0. Well, I could try to simplify this, but since I have this addition in the denominator, it won't do me any good. I will just have to use the quotient rule. So that would be the derivative of the top. Sorry, that would be, whoa. The derivative of the top, which would be negative 2 minus 2x, times the bottom. Use a lot of parentheses when you're doing the quotient rule. Minus the derivative of the bottom, times the top, all over the bottom squared. And can you simplify this? Sure, I'm sure you could. And go ahead and do it if you want to do that. But all I know is that if I'm plugging in 0, that's going to be an easy calculation to do. I'll just have -2 times -1 in my first thing. I'll have 0 times all this stuff over here, which I don't really care is, but it ends up being 3. And that would be divided by -1 squared, which is 1, giving me an answer of 2. That is my tangent slope of that function at 0. Let's do the other one. Let me shrink this. I want to find g prime at 0. I can't simplify this. I have to use the quotient rule. Take the derivative of the top. I guess this should be an x. I don't know why I have keys. Just use an x. So that's 3x squared times the bottom, -2 cos x, minus the derivative of the bottom. That would be -2 sine x times the top, x cubed, all over the bottom squared. Okay, and again, I could simplify it if I wanted to, but if I'm just plugging in a value, I could do that. That'd be 0 minus 0 over, this would be -2 squared, 4, which is 0. Okay, done. All right, now to some questions with more application. So let's find where this function has a horizontal tangent. So horizontal tangent, slope is equal to 0. We're going to have to figure out when f prime equals 0. So I will start by first taking the derivative using the quotient rule. And I set that equal to 0. Well, if we think about when something is equal to 0, all we care about is that the numerator is equal to 0. The denominator can be any number. The key is the denominator can't be 0. So if I had a situation when like x is 1, well then I can't have our number 1 because that's going to be a discontinuity. Here we can see the function x equals 1 would be an asymptote. So we're looking for values for x that are not 1 to have a vertical asymptote. So I just need to figure out when the numerator equals 0 and make sure that that value is not 1. So the numerator set equal to 0 would be 2x, x minus 1, minus x squared set equal to 0. Or 2x squared minus 2x minus x squared equals 0. 2x squared minus an x squared is just an x squared minus 2x equals 0. I'll factor out an x. I'll get x times x minus 2 equals 0, and I find two locations, 0 and 2. Okay, that is good. It is not 1. It's two different locations at 0 and at 2. We will have a horizontal asymptote, so long as my math is correct, and I believe it is. Okay, so that is how we solve some fractions set equal to 0. Here's a good question. We have the position of the particle is given by x of t. What is the position of the particle when it is at rest? Ooh, this is tough, but it's very important to realize what rest means. Rest means we are not moving, or the velocity is equal to 0. So for this problem, to accomplish this, I will have to find x of t when v of t equals 0. Where am I? All right, so first I need to figure out when v of t is equal to 0. I will have to find x prime of t, which is equal to v of t if we remember our calculus and physics relationships. And that would be using the quotient rule. Derivative of the top times the bottom minus the derivative of the bottom, just 2t times the top, over the bottom squared. Okay, and if we look at this, we wouldn't have a position at root 7 because then we'd have a vertical asymptote. So it's a situation where this particle at a certain time does not exist. So we're probably going to be talking about times that are greater than probably root 7. Who knows? I'm not sure if the problem is designed perfectly, but let's just go with it. This is my position function. I will figure out when that's equal to, this is my velocity function or my x prime function. I'll figure out when that's equal to 0. Okay? I will just worry about the denominator equal to 0. I will make sure that the denominator doesn't equal 0. So I'll have t squared minus 7 minus 2t times t minus 4. Now what I like to do is change this to plus a negative before I distribute. And I'll get t squared minus 7 plus negative 2t squared plus 8t, which is equal to 0. This will be negative t squared plus 8t minus 7 equals 0. I don't like that negative t squared, so I'm going to multiply everything by a negative 1. And now I see I have something that I can factor to solve. I will get t minus 7, t minus 1. And that will give me two values when t is 1 and when t is 7. Now, most likely we were thinking about values that t are greater than root 7. So I would probably exclude 1 and just talk about 7. Let's just find if we can find the velocity at both of these times. So this is the time when my velocity is equal to 0. The question is, what is the position? Okay, not the velocity, of course, the velocity is 0. What is the position when the particle is at rest? This are the times when the particle is rest. We will need to find my position at those times. I plug in 1 minus 4 over 1 minus 7. I get negative 3 over negative 6, which is 1/2. And my position at time 7, that will be 7 minus 4 over 16 minus 7. This will be 3 over 9, which is 1/3. Okay, so those are my positions. Those are the answers to my question. Two more questions. Find the equation of the line normal to f of x when x is 0. Normal is just the same as perpendicular. So if my slope of my tangent equals 3, the normal slope would equal negative 1/3. Opposite reciprocal slopes, or slope is equal to negative 1 over the slope of a perpendicular. Okay. All right, so find the equation of the line normal of f when x is 0. So first I'm going to find the point when f is at 0. And I get 1 over 6. Okay, so that's the point on my equation where I need my tangent line or my normal line. So I need to find my slope generator by using the quotient rule. Derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. And what I get is this. And I can just plug in 0 to find the slope of the tangent at 0. I get 6 minus 1 over 36. That is 5/36, which means the slope of my normal would be negative 36/5. And using that and my point, I'll have my equation. Y minus 1/6 is equal to negative 36/5, x minus 0. And finish off with this problem. Given the position, find the exact velocity at the time t equals 1. I put this problem in here for a reason. Okay? A very specific reason. And the specific reason is that Once you know the quotient rule, you're going to think, I should use the quotient rule everywhere, whenever I see a fraction. However, if I see something like this, watch how easy it's going to be for me to simplify this. And then take the derivative. And this is going to be the derivative at 1, at 2, at any single location. You're not going to get such a nice answer if you use the quotient rule. You'll get an answer and you'll get 6/7 no matter what you plug in. But this is just an example of always look to see if you can simplify. And after you look, you'll get your answers potentially in an easier way than if you went and did the quotient rule. Okay? That's it. Thank you very much.